This video contains some notes for section 5.7, which is about the mean value theorem, which we will come to refer to as the MVT, not to be confused with the intermediate value theorem, which we already know. You might pause for a second and go back and look that up in your notes if you don't remember what that said. Now, just before we go any further, this mean here, this is not as in the angry value theorem. This is mean as in average, okay? So when we think of average, we think of, in calculus terms, the average rate of change of something. That's when we find the actual slope of a secant line, right? Using 2 points instead of tangent line using 1 point. That'll help us help motivate what this is about. But before we do that, we're going to talk about a simpler version called Rolle's theorem. Which says that if a function is continuous on a closed interval from a to b, and this is a big and, this is the first time we've had a theorem that required something to be differentiable. Here, the mean value theorem, you have to have a continuous function, right? But this time, we're going to also require that the function is differentiable and it's got to be differentiable only on the open interval. It doesn't have to excuse me, it doesn't have to be differentiable at the endpoints. It's like a technicality. It doesn't really make a big difference to us, but you can think of counterexamples and things if you're interested in that. So this time it's got to be continuous and differentiable. And there's one more condition here. And for some point f of a, for the endpoints, f of a is equal to f of b. In other words, the height of the function is the same at the endpoints. Then there's a point, there's some value c in that interval such that f prime of c is equal to 0. Okay, that's what it says. Now let's draw a picture and see if we can make sense of that. So here's some function. Now notice that I'm drawing the points at the same height. Well, that was one of the conditions of the theorem. F of a equals f of b. Now, there's a lot of ways I can get from here to here. And of course you can't double back, right? It's got to be a function. But it has to be continuous and it's got to be differentiable, which means no jumps, holes, or vertical asymptotes. And what does differentiability mean? That means no sharp corners. And that's key for both of the theorems that we're going to talk about here. So if you're getting from here to here, if you're getting from here back to here, then there must be a place in between where the derivative is 0. So we have a maximum. We could have gone this way, right? But I challenge you to try to draw a function that goes from here to here. It's continuous, no holes, jumps, or vertical asymptotes, and is differentiable, no sharp corners, and doesn't manage to have a maximum or minimum. You can't do it. So here we found a spot where the derivative of the f function at this point would be 0 because we found a maximum or a minimum. We could have gone this way and found a minimum, but it's got to have a genuine horizontal tangent line if it's differentiable. Does it really have to be differentiable? Well, sure, because if it's not differentiable, then we can very easily come up with a counterexample. If you want a counterexample, then you have to make something that's obviously not differentiable at some point here. So here's a function that satisfies the condition. Is it continuous? Sure, you can draw that without taking your pen off the paper. Is f of a equal to f of b? Yep, they're on the same line there. Does it have a spot where the derivative is 0? No, it doesn't. The derivative is like, I don't know, 1-ish here, negative 1-ish through here, and undefined here. So it's not differentiable. It doesn't actually make it here. It's got to be differentiable for the theorem to work. Okay, so this doesn't work. All right. Now, an extension of that theorem, and more important, is the mean value theorem. And I'm going to state the theorem, and I'm going to challenge you to think about, pause the video, and think about what this means. And it's not too terribly different from Rolle's theorem. Okay? It says this. Starts very much the same way. If f of x is continuous on the closed interval from a to b, closed interval, and differentiable on the open interval ab, then there is a point C in that open interval such that f prime of C is equal to f of b minus f of a over b minus a. Now, you can pause for a second, study this for a minute, maybe draw a picture, okay? But I really would like you to do that. Okay, so you're back. Now let's draw a picture and see what this is trying to tell us. So here's some continuous and differentiable function. Let's say this is a here, this is b. Right, so this is the point a comma f of a. This is the point b comma f of b. Now, what's this part of this expression? F of b minus f of a over b minus a. Well, this is a slope, right? This is y minus y over x minus x. The slope of the secant line that connects these 2 points, right? Y minus y, or x minus x, that would be the slope of this line, right? This expression right here is simply the expression for the slope of this line. Okay, so the mean value theorem says if this function that gets from here to here manages to do it in such a way that it's continuous and differentiable, right? No holes, jumps, vertical asymptotes, and also no sharp corners, then there must be some point here in between here and here where the derivative of the function at this point is equal to the slope of that secant line. So maybe pause for a second again, look at the picture and see if you can spot where that point is in this for this function. Okay, so I think right around here, if you thought right around here, it looks like we would have a tangent line that has the same slope as that secant line. So here, there's our C, right? And at this point, the derivative of the function, the slope of the tangent line, is equal to the slope of the secant line. And that's, I think, a great way to understand this theorem, or sort of summarize it with words to say that if a function is continuous and differentiable, those are our criteria, then instantaneous rate of change, in other words, the derivative, is equal to average rate of change, which is the slope of a secant line. Right? So somewhere slope of tangent line must equal slope of secant line. When is that true? If a function is continuous and differentiable, then it must be true. You could draw a function that has a sharp corner in it, just like our example for our counterexample for Rolle's theorem, and you'll see that it does not have to satisfy the mean value theorem. So, what do we do with this? Here's the classic type of mean value theorem problem. So let's take a function like y is equal to the square root of x. Oh, let's make it more interesting. 2x minus 1. And we want to find the c that is guaranteed by the mean value theorem. Oh, by the way, did you figure out why it was called the mean value theorem? Because this is the average rate of change. So find the c guaranteed by the mean value theorem on the interval, let's say 1 to 5. Well, what are we supposed to do here? Here's our interval from 1 to 5, so we need to find the average slope here, and then we need to find the derivative and find the value where the derivative is equal to the average slope. So this is the missing piece for us here, right? So let's find the points. Our points are the points 1 comma, what do we get when we plug 1 into this? 2 times 1 minus 1 is 1. The square root of that is 1. And the second point, we plug 5 into this. 2 times 5 is 10 minus 1 is 9. The square root of 9 is 3. So the points are 1, 1 and 5, 3. So the slope is y minus y over x minus x, which is 2/4 or 1/2. Okay, we just found this. We just found our average slope. Now, there's supposed to be some value, if we find the derivative, there's supposed to be some value where somewhere between 1 and 5, the derivative is actually equal to that. So let's find the derivative. Y prime is equal to 1/2 times 2x minus 1 to the negative 1/2 times the derivative of what's inside. Please don't forget the chain rule. And the 2 and the 1/2 cancel out, so that gives me 2x minus 1 to the negative 1/2. So, mean value theorem says somewhere in this interval between 1 and 5, this should be equal to this. The derivative should be equal to the average slope. So let's write that. I'm going to just replace the x with a c. You don't have to do that, but just to motivate we're trying to find the c, right? So you could leave it as an x. Either way, you're finding the right number. Okay, so I have set the derivative equal to the average rate. All right, so let's see. How do you get rid of the negative 1/2? You'd have to raise both sides to the negative 2 power, right? So 2c minus 1 to the negative 1/2 to the negative 2, right? Because we multiply these exponents, and that would give me 1 here, equal to 1/2 to the negative 2. that gives me those exponents cancel, so I get 2c minus 1 is equal to 1/2 squared is 1/4. The negative flips it over to 4. So 2c is equal to 5. C is equal to 5/2. And that's good. We were looking for an answer. It better be in between 1 and 5. And of course 2.5 is between 1 and 5. So what does that mean? It means that if you connect the 1 and the 5 on this function, in other words, if you connect these 2 points, this is the place where the derivative is parallel to, has the same slope as that secant line. That's what we found. Some implications of the mean value theorem. If the classic example is the speeding car. So sometimes in Virginia, for example, it's legal for police to track your speed from the air. And you may have noticed on various interstates that sometimes there are these big white lines painted across the road. And that's so that the helicopters or whatever aerial patrols can figure out where your car is. Those are specifically spaced at either like a quarter mile or half mile or mile intervals. So let's say you pass one of those at 0 seconds. They start the clock on you, and you pass the second one 20 seconds later. And in that distance, you have gone half a mile. And let's see, so how much have you covered? You've covered 1/2 a mile in 20 seconds. So that would give us 0.5 divided by 20. It says 0.025 miles per second. Of course, the speed limit's not in miles per second, so we just convert that. There are 60 seconds in a minute and 60 minutes in an hour. That'll get us miles per hour. So 0.025 times 60 and then times 60 again gives us 90 miles per hour. So the Virginia State Patrol sends you a ticket in the mail for speeding, for going 90 miles an hour in a 70 zone, which, by the way, is criminal speeding because it's over 15 miles over the speed limit. Don't want to get caught for doing that. And you go to court and you make the argument that, listen, this is being tracked by a helicopter. Nobody was on the ground with a radar gun. How do they know that, in fact, you were ever going 90 miles an hour? Right? I mean, you could have been going 60 part of the time. Maybe you were even going faster than 90 miles per hour. But how do they have any right to give you a ticket for 90 miles an hour when all they figured out is your average speed? And if they know what they're doing, they can say, well, because of the mean value theorem, right, that you learn in calculus, your speed is a continuous function. Your car cannot like suddenly change from one speed to another one. In other words, your position function can't look like this. Zoomed in on this, it would have to be a rounded corner like this. You can't very suddenly go from one speed to another. You could imagine like the dial on your speedometer, if you still have one of those. It can't suddenly go from here to here. It has to cross every value in between. In other words, it's a continuous differentiable function, your speed. So What does that mean? It means that the mean value theorem applies. It means that if your average speed is 90 miles an hour, somewhere in this 20-second interval, you had to be going exactly 90. You could have been going slower and then faster, but somewhere in that interval, your average speed had to be equal to your instantaneous speed. Therefore, they have every justification in writing you a ticket for 90 miles per hour. In all probability, you were probably going a little faster than that at some point, but they don't know that. They do know, because of the mean value theorem, that you had to be going 90 at some point in that interval.